Hello everyone and welcome to the session. It's Houtan here, and as you can see, I'm broadcasting from my house in Melbourne in lockdown. We're going to be covering the topic of machine learning, and our focus is going to be on getting you as close as possible to using ML in your day-to-day work. In this session, we're going to get more technical and dive a little bit deeper with detailed examples of how you can incorporate the benefits of ML into your organization. And of course, we'll finish up with an end-to-end, step-by-step example for getting started with object detection in GIS, so stick around because the next 20 minutes are going to be very interesting. Our session today is going to kick off with what I'd like to call a 1-minute overview of machine learning. Next, we'll explore the different categories of ML in GIS and some of their most typical use cases, which could be helpful to your day-to-day work. We'll follow that with a bit of a more technical look at how ML and GIS work together in terms of a workflow. We'll then put that workflow to use in a practical example with aerial imagery. And finally, we'll wrap up our session by covering your best and most immediate next steps for getting started with ML. Okay, let's do it. A 1-minute overview of machine learning. The first thing that I want to make very clear is that ML or AI or GeoAI is a tool. It's not an end result in and of itself. It's a means of getting there. And while ML is a powerful and adaptable tool to use, it's not automatically the best tool for every single GIS task. It's not a silver bullet. It may very well be that the tasks that you're looking to accomplish can be done more accurately and more efficiently using another GIS or geoprocessing workflow. Now, that being said, in my opinion, there's never been a better time to consider using ML in your day-to-day work because ML tools are more integrated into the ArcGIS platform and easier to use than ever. There are plenty of examples and support for using ML within the Esri ecosystem, and computing power is more available and cheaper to use than it's ever been. The field of machine learning is changing at such a rapid pace. New models and techniques are being developed every month, so this section aims to provide the most recent interpretation of where GIS needs and ML techniques intersect in October of 2020. Today, we can break up the use of ML in GIS within 7 major categories. The first 2 sections are all about objects. You can use ML to detect objects and then further classify those detected objects into different categories. A good example of this could be using ML and high-resolution aerial imagery to detect swimming pools in backyards, and then taking those detected pools and further classifying them into well-maintained pools that would look blue and clear, and neglected pools that would look green and murky. Another example of object classification could be in an insurance or disaster recovery context, where different houses can be classified as damaged or not damaged. Object detection is also useful in a utility context, where imagery can be used to detect man-made objects that are at risk of encroaching our pipelines, or vegetation that could be growing dangerously close to our power lines. Object detection is probably the most ubiquitous use of ML in GIS, and it tends to fit in well within existing GIS workflows. The next 2 categories are all about points and pixels. The concept of pixel classification has been around for a long time in GIS, and what ML brings to the table is automation of this process through the concept of semantic segmentation. A classic example here is land cover classification, where specific pixels are labeled as forests, agricultural land, or buildings. Taking this concept a step further, higher quality data can be combined with pixel classification in ML to extract building footprints as well as road center lines as GIS features. Similarly, the concept of segmentation can be used in the 3D space with point clouds. So each point in a point cloud can be assigned a label representing a real-world entity such as buildings, ground, and trees. Similarly labeled point clouds can then be clustered together to form objects such as a single tree, and secondary GIS workflows can then be run on those 3D objects to perform tasks such as identifying the height of the tree or estimating the tree canopy circumference. The final 3 categories stray a bit from our traditional concept of GIS. We're talking about image enhancement, tabular data, and unstructured text. Image enhancement is exactly what it sounds like. A trained model can be used to synthesize high-resolution imagery from lower-quality data. Remembering that we need a high-quality version of the imagery to train the model on first, this technique could be useful when working with composite imagery services, where certain regions are provided in higher resolution and certain regions are lower resolution. Tabular or non-spatial data can be used in the context of deep neural networks in ML, and the results can then be tied back into the spatial world. So an example of using tabular data could be predicting the output of a solar farm based on climate information for the region. And finally, we now have the ability to run ML and natural language processing with the goal of extracting geospatially located features from text. So a good example of this would be extracting spatial features from the text of digitized reports. Now that we have an understanding of the capabilities of ML, let's get a little bit more technical and cover how ML can fit into your existing GIS workflows. Perhaps the easiest and most straightforward ML workflow is typically the one we'd be using for developing POCs or proofs of concept. There are three main components to this workflow. Step one is done in ArcGIS Pro. This step is all about generating our training data. So what we want to do is to import the imagery for our area of interest into Pro, and then use the Label Objects for Deep Learning tool to label and then export a good number of training samples. Step 2 is typically done outside of ArcGIS in a Python environment. Jupyter Notebooks is the tool of choice in this scenario because it lets you run your Python code line by line and allows you to see results at every step. Over the past year, Esri has made great strides in incorporating Python directly into the different products, so you have the option of using the integrated Jupyter Notebooks that's within ArcGIS Pro, or even using ArcGIS Notebooks itself in your enterprise deployment. Regardless of the Python environment you choose, this is the step where the training of the actual ML model happens. To do that, we need to use one of the open source machine learning engines that's incorporated into the ArcGIS API for Python. You can find the full list of these tools under the arcgis.learn module in the API documentation. It's good to note that training the model is a very heavy task and requires a capable machine, so I'd recommend using a cloud-based virtual machine with 6 or more processing cores and at least 30 gigabytes of RAM for this step. The output of this step is a trained model definition. Finally, we bring that model definition back into ArcGIS Pro and use the Detect Objects Using Deep Learning tool to apply our trained model to the entire imagery dataset and view our detected objects as GIS features. Now, once you have the system down and you'd like to use ML in a more automated and repeatable pattern, your workflow can be adapted to look something like this. So the first two steps stay the same, where we end up with a trained model definition. But once we have that model definition, we can set up a data pipeline where fresh imagery is brought in cyclically. Now, this can be imagery from aerial capture or drones or from an imagery provider. And you just have to make sure that it's the same type of imagery that the model was trained on. Then, the ArcGIS image server will step in to perform the inferencing of our results with our model definition. Using the image server allows for the process to be much more automated and driven on a schedule that matches your business workflow needs. Awesome. Now that we know what ML is capable of and what the workflow looks like, we can walk through a practical example. State and local governments in Australia put new laws and registries in place from time to time with the goal of protecting residents from injuries. An example of such regulations might include providing adequate fencing around backyard swimming pools. In our scenario, however, our fictitious local government council is interested in identifying houses with trampolines in the backyard. Now, for anyone who might not be familiar with trampolines, here's an example. They're a device used for recreational or competitive bouncing. This is an example of an early trampoline-like device called a blanket toss by the Inuit people of Alaska in North America. And here are some more examples of competitive trampolining at the Olympics and other national and international competitions. So needless to say, trampolines can be both fun and hazardous, and it's no surprise that our fictitious local government council is interested in maintaining an up-to-date registry of houses with trampolines. We're going to use imagery by Jacobs Group Australia and the Australian Capital Territory to first train an object detection model, and then use that model to automatically detect all the backyard trampolines in our region. Let's get started. All right, so the first thing we'll notice is that I'm in a virtualized environment here, and it has quite good specs, so I can go ahead and hit Control-Shift-Escape, and we'll jump into the Performance tab. You can see that this machine happens to have 12 virtualized processors, and it has 112 gigabytes of RAM. So these are the kinds of specs that'll come in handy once we're training our model and then performing our inferencing. So as you remember, the first thing you want to do is you want to install ArcGIS Pro, and that's exactly what I've done here. So after you install ArcGIS Pro, you'll know that there's a specific version of Python that gets installed onto your machine that has probably half the tools that we're going to need for this exercise. So what we can do is we can go ahead into our Project tab in ArcGIS Pro, and then go down here to the Python tab, and we'll be able to see the Python environment that's come pre-installed with ArcGIS Pro. Now in here you can see that there is a Python environment there that I've cloned, and that's exactly what you need to do. So if you hit that Manage Environment button, you'll be able to take the original ArcGIS Pro Python 3 and you'll hit that clone button and you'll be able to create a clone of it. And once you set this cloned environment as your active environment, you'll then be able to go ahead and install all the specific libraries that you need, and you'll be able to work within here without having any chance of affecting the original Python environment. In fact, that's actually the next step. That's the next thing that we need to do. So after you switch over to that new environment, you'll need to go ahead and navigate over to the ArcGIS API for Python. I've included a link of this in the slides. And you'll just want to follow the install and setup instructions over here. So find out which of these applies the most to you. So perhaps you'll want to go over here in the update the ArcGIS packages, ArcGIS Pro 2.2 and above, and just follow the instructions that are included down here to install and update all the packages that you'll need in order to run your machine learning tools. So jumping back into our ArcGIS Pro project here, you'll notice that in my fictitious console, I actually have two chunks of imagery here that I'm going to be working with. So the great thing about this is that I'm going to use one section of my imagery to do my training, and I'm going to keep the other one completely untouched as essentially as my validation set. So I'll just go ahead and turn that guy off, and let's go and have a zoom in and take a look at the quality of this suburban aerial imagery, courtesy of Jacobs and the ACT government. Now, the first thing that I noticed is that within this residential neighborhood in the ACT, you can see that there are quite a few backyard trampolines that are either completely or partially visible in people's backyards. So this is actually quite a good training data set for us to be using in order to train a model with. There you go, there's another one over there. So in order to do that, we're going to go ahead and use the first tool of interest in order to create our training sample. So with the right set of imagery selected here, this is our 102 imagery, I'm going to go ahead and jump into the imagery tab. And under the imagery tools, we have the classification tools right here. And from there, we want to go and grab the label objects for deep learning tool. And once we do that, we can see this thing pop up right here. So within here, first thing we want to do is we want to add a new class for our trampoline objects that we're detecting. So we'll just go ahead and type trampoline, and we'll give that a value of 1. We'll go ahead and select a color. And once we're done, we'll hit OK. And then we have a variety of tools here that we can use to start selecting our training sample. So let me just zoom into a section of suburbia right here that we can see a couple of examples of circular trampolines. I'll go ahead and pick the circular tool and start out from the center all the way out to the radius. So you can see I just selected one sample right there. That's a training sample for the trampoline. I'll just go ahead and select another one and another one, and I'll keep panning and zooming around this imagery until I have a good number of these training samples selected. In fact, if I zoom out just a little bit, I'll show you what I did earlier. There we go. So all of these circles that you see around my imagery, these are all the different trampolines that I grabbed as my training samples. In fact, to make this seem a little bit more visible as well, I'll just go ahead and turn this off. You can see all of these are the training samples that I created. Now, once we're happy with this, we can go ahead, and we have quite a few number of these. We can go ahead and hit the Export Training Data tab right over here. We'll pick an output folder. We don't need to mask our polygon features right now for this scenario. We want to go ahead and change the output format to PNG because that's the format that our that our tool is going to be using later on. And here we get to set the tile size. So this is the X and Y of the different image chips that are going to have the trampolines in them. So when I did this exporting, I actually decided to experiment a little bit. So the first set I exported as 256 by 256 tiles. And the second set, I actually went a little bit smaller and did 128 by 128 tiles. So the tiles were smaller, and I guess in comparison, the trampolines within those tiles were much larger. And I'll show you the difference between these two when we get to our notebooks there. And the final thing that we want to select here is we want the Pascal VOC as our metadata format. So once you're happy with all of that, you can hit that run button. And the output of this tool, if I just go ahead and jump into my Pro project over here, the output of this tool is a set of labeled objects. So when I did the labeling at 256 PNGs, I can jump into the image tab here, select one of this, and we will see all the different image chips that were created that have some sort of trampoline in them. So these are the 256 by 256 images. And of course, we can jump back up here and look at the 128 by 128 images as well. So you can see the images are much smaller, and relatively speaking, the trampolines occupy a larger portion of each of these image chips. Okay, so now that our training data is created and ready to go, we can go ahead and start up our Jupyter Notebook. So the way that we do that is we'll go into our Start menu and we'll hit the Python command prompt button. And we'll make sure that the right ArcGIS Pro Python environment is selected, which is a cloned Python environment in this case. And we'll type in Jupyter Notebook. And what this will do is it'll spin up the Jupyter kernel, and it will open up our Jupyter Notebook. So I've created two different Jupyter notebooks here, one to deal with my 256 images and one to deal with my 128. And these are pretty much identical copies of each other. So I'll go ahead and open up the 256 right now, and we can step through it. So the first thing that we want to do is we want to go ahead and import a couple of different libraries from the ArcGIS.learn module. So we'll go ahead and import the prepare_data, and we'll go ahead and point to our data path, which in this case are our image samples, so 256 PNGs. And we'll put the chip size down here, and we'll assign that to the variable data. And then we'll be able to go ahead and confirm that the data was loaded correctly, looking at different classes in our data and visualizing a specific batch of our data. So you can see we've got the one class of trampoline over here, and you can see everything is correctly labeled in our training data. Then we can come down further and we can start our training. So what we need to do is we need to import the single shot detector library from our ArcGIS.learn module in here. And within that single shot detector, we need to set a couple of different parameters. So if we go up here and have a slightly closer look at the way that our training samples are set up, we can sort of approximate that each of these trampolines would probably fall within a 4x4 grid in this imagery. So we'll go ahead and set that grids to a value of 4. You can see that mostly speaking, the trampolines are of a uniform size in the backyards without too much variation. So we'll go ahead and set the zooms level to 1.0. And since we're only interested in circular trampolines instead of larger rectangular ones, the ratio of the shape of our trampolines is going to be a 1x1. It's all going to be squares, or really circles in this case. So we'll go ahead and set that to 1x1. And sure enough, if we go and use the show results function over here, we'll be able to see on the left-hand side our training sample, and on the right-hand side what the machine is guessing a trampoline would look like without having trained the model. So you can see we went with a 4x4 grid, and the sizes typically seem to match up over here. We'll go ahead and scroll down, and the next thing that we need to do is we need to find a learning rate, again using the learning rate finder in the ArcGIS.learn libraries. So we'll use this learning rate finder function, and it automatically goes ahead and extracts the ideal learning rate for our model. And it's always going to be something between 0 and 1. Now that we have our learning rate, we can use the single shot detector.fit to train our actual model. So before running this for 100 epochs, I ran it for 10 just to kind of get an idea of the way that the model behaves. Then I ran it for 100 epochs, and the thing that you're looking for here is this training loss and the validation loss consistently decreasing. In fact, after you've done running your training here, you can use this plot losses function to be able to see what the losses look like, and you can see the losses are decreasing quite uniformly, and this is what we're looking for down here. Now that a model is trained, we can use the average precision score function over here, and we can see that we're getting an average of about 77.13, 77.14% accuracy compared to our training data, which is not bad at all. I mean, this is the averaged out precision score. We can always get more specific later within a GIS context once we import the model back into ArcGIS Pro. So we can go ahead and have a look at some of the trained samples over here. So the left-hand side is our training samples, and the right-hand side is what the machine was able to detect as a trampoline. You can see, for the most part, it's really quite good at finding the trampolines here. You might notice a mistake here and there. Yeah, for example here. But you'll know that for the most part, it's actually doing quite well. So what we can do is we can go ahead and save our model for the 256 pixel case at 100 iterations. You can see that model is saved. Now, something else that I did is sometimes I found out that doing more training is actually a better idea. So we went ahead and trained it for 300 epochs as well. So all the settings are exactly the same. It's just instead of doing 100 rounds of training, we're doing 300. And I let that run again for a while. And you can see that our training loss is still decreasing, but it's a lot more jagged. So right around down here, we might start to run into overfitting issues. But again, for the most part, it still seems to be doing okay. And the precision is actually just a little bit lower here as well, 73% instead of the 77. And if we have a look at the predictions, again, they look pretty good, but you'll still spot mistakes here and there. There we go. So it's kind of detected two things down here, whereas only one of them is actually a trampoline. But regardless, we went ahead and we saved this model anyway. And that's what I did for the 128 pixel example as well. I ran it for 100 iterations, and then I ran it again for 300 iterations and saved those models. So now that we have 4 different trained models, we can jump back into our ArcGIS Pro, and we can start to use these models not only on our training data set here. Just go ahead and close that. We don't need this anymore. But also on our validation imagery data set, which is that set over here. So in order to run those tools, we jump into the analysis tab right there. We'll hit that tools button. And provided you have the image analyst extension installed, you can just search for detect objects. There we go. And we get this detect objects using deep learning. You can see it's part of the image analyst toolbox. And once this tool loads, we'll be able to point it to our raster where we want to be doing our detection. So in this case, this is the 103 raster at the top over here. And we'll also be pointing it to our model. So I'm just going to go ahead and select this. The input raster is going to be our 103. And we can give the detected objects a name. And then for our model definition, we go ahead and browse. Here we go, labeled objects, trampolines, the 256 model, for example, under the models tab, you can see that this is the 256 models at 100 epochs and at 300 epochs. So if we go ahead, select the 300 epochs EMD file right here, that'll be pulled in and it'll start to fill in the arguments with their default values. And that's what we're looking for here, is those default value arguments. Okay, so we can see right here the arguments that are pre-filled in based on our trained model. Specifically, we want to pay attention to the padding value over here. And once we're ready, we can hit this run button. And what'll happen is it'll start to detect objects and pull them into ArcGIS as features. So in fact, if I just go over here and grab the ACT 103-256, and turn this layer on, we can just go ahead and zoom in and see all the different trampolines that were detected using our machine learning algorithm in people's backyards. So if we have a zoom in over here, we can see that, yep, that's a trampoline, but it's also sometimes detecting people's cars in the driveway. So it's definitely not the perfect model, but it is also doing a pretty good job. There we go. These are all different backyard trampolines. And if I was to select one of these features, you'll be able to see that's a 99% confidence that that's a trampoline. Whereas if we're looking at the car, it's about 75% confident that that's a trampoline. So overall, not too bad. Okay, so now that we have our features, we can start to use GIS workflows here to start to essentially weed out the ones that we know for a fact aren't going to be trampolines. So, for example, we've detected some cars here on the highway. We're not really interested in that. We know that all of our trampolines will be falling within a specific land parcel in our example here. So what I've done is I've gone ahead and I've used the Open Data Portal for the ACT and reached out to the ACT blocks layer, which is what the parcels are located in. And using that map server link, I was able to pull that information directly in here. So if I just go ahead and turn off this piece of imagery and instead turn on my ACT blocks, there we go. You'll be able to see the specific parcel sections and where those trampolines would fall within. And then we can, of course, take this a step further. We can either do the analysis ourselves or maybe give it off to a teammate to do further analysis where they could perhaps weed out all the trampolines that fall outside of a specific confidence interval, or perhaps grab the centroid of each of these polygons and place it within the different parcels in order to note whether a specific land parcel has a trampoline or not. In fact, a colleague of mine, Simon, was just able to do exactly that. So if I grab the trampoline layer that he put together, yeah, that's okay. We'll be able to see, let me just go ahead and turn off my other layers here for better visibility. We'll be able to see that he was able to do some analysis in here and essentially highlight which of the houses had a trampoline within them. So if I select this one, you can see that, yep, does it have a trampoline? Yes, with that kind of a confidence. This one as well, etc., etc. And in fact, what we ended up doing is we did that for the entire two sections of our imagery here. And this is something that we can quite easily pull out and publish to our portal and use, for example, within a dashboard or within a web map or a web app and run further analysis on it. Okay, so that's the end of the demonstration. Let's jump back into the slides and continue. That was pretty awesome, right? I always like to say that when object detection is done right, it almost feels a little bit like magic. Now, if you've been inspired by this demo and want to try it out for yourself, here are your next best steps for getting started with ML. First, you want to think of a real problem or a real use case that you currently have in your day-to-day work that you think could be improved by the use of one of the 7 ML techniques we covered earlier. Now, as you remember, ML is a tool, it's not an end result. So for your project to be successful in your organization, ML should be used to serve a real purpose and solve a real problem. Once you have your problem in mind, you should head over to developers.arcgis.com and look under the Sample Python Notebooks section for the closest example that relates to your problem. You're going to be using the sample notebook as a template to apply to your own data. And the last thing left to do is to spin up an environment and run your proof of concept. You should install ArcGIS Pro and the relevant extensions that are required. So for example, object detection would require the image analyst extension. And you should use the install and setup guide for the Python API to install the required Python libraries for your project. And then follow the step-by-step instructions in your selected notebook to get your results. That's it. Simple as that. Now, I hope you enjoyed this presentation and that it inspired you to try out ML for yourself. You can find a summary of the resources that were covered during the session here. And if you have any questions, you can reach out to me at hemad@esriaustralia.com.au or find me on LinkedIn. We'll catch you later.